you are asked to determine the specific latent heat of vaporization of water using the method of mixture. The figure shows a copper boiler used in laboratory to generate steam. The rubber tube B is used to take steam out, and insulated copper calorimeter and a copper styler are also provided. Part A1, if the level of water in the boiler is not sufficient, how do you identify? It is using the tube A. I will draw the rough sketch of the given diagram. Here is the boiler. We are using it to generate steam. There is a tube like this. It is tube A. We have to use the water level such that this tube A is immersed in water. This tube A is used to maintain the atmospheric pressure in the container. But if the water level is below the tube A, we can't do the practical by using this apparatus setup, because of when heating this system, the generated steam will be flow out through the tube A. But we have to get steam through this rubber tube. Then we can identify that we have used appropriate water level. By using tube A, we can identify if water level is not sufficient. If water level is not sufficient, steam will flow out through the tube A. It is the answer for A part 1. In part 2, after rectifying the defect in part A1 above, steam is generated in the boiler. If the rubber tube taking the steam out is blocked, how do you identify it? We can see that hot water is flowing out through the rubber tube when the system is boiling. Then we can write answer for part 2. Hot water will come out through the tube A. Tube A. If the rubber tube is blocked, there is no method to bring water out of the out to the system. Then we can see that this boiled water is come out through the tube A. Then part B, it is not correct to mix the steam coming out to the tube B directly with water in this experiment. Part 1 due reason. If you are using this tube directly to mix steam with water in the calorimeter, the condensed water will be mixed with water in calorimeter. Therefore, we have to write the reason. B part 1, condensed water will be mixed with water in calorimeter. We have to mix only vapor, water vapor come out through the tube B. But if we are using tube B directly to mix vapor, the condensed water will be mixed with water in this copper calorimeter. Then part 2, how do you correct it? We have to use the steam tap by using the steam tap. Steam tap means we can connect a container like this. In the steam tap, we have to use the inlet from upper end, and in lower end there is a tube which is bending like this. Now the condensed water will be collected this lower surface of this steam tap, and only the water vapor will be mixed with this water in the container. We have to write only the method. They have not asked to do. Then part C, what are the other two measuring instruments that you need for this experiment? We have to use a balance to measure the masses in calorimeter. Mass of empty calorimeter, mass of calorimeter with initial water volume, and mass of system after mixing vapor. Therefore, we have to use a balance. We can write an electronic balance. We are normally using an electronic balance, but if you have written that a chemical balance, triple beam balance, or 4-beam balance, it is also correct. We have to use a thermometer. They have provided a thermometer in this calorimeter, but we have to use another thermometer with this steam generator. Then we can write another thermometer. This thermometer is given, but they have not given this one. Then part D, after making the correction mentioned in part B2 above, you pass the steam into water in the calorimeter. How do you correctly keep the end of the glass tube which passes steam? Underline the correct procedure just above the water level, touching the water level, below the water level. When mixing, steam comes out from this glass tube. We have to maintain the end of this glass tube just above the water level. Then answer for part D, you have to underline just above the water level. Because of, if we are trying to mix vapor, if the end of the tube is not just before, just above the water level, if it is touching the water level, vapor will not mix correctly. When mixing vapor, it will condense due to condense before mixing. And if the end of the tube is below the water level, we can see same thing. The water vapor will condense before the before mixing. Then part E, what are the temperature measurements that you expect to take in this experiment? Give them in order of measurement. First measurement, theta 1, is the initial temperature of water in calorimeter. And second measurement, the maximum temperature reached by the water in calorimeter. But we can write, before get that two readings, we have to confirm that the temperature of steam generated by steam generator is 100 degrees. Therefore, we have to get temperature reading of this thermometer first. Then we can write theta 1 should be temperature of steam. Theta 2 reading, initial temperature of water in calorimeter. Then final reading, the maximum temperature of water and vapor mixture in calorimeter. You have to write this order. It is the order of reading. In part F, in addition to the above temperature measurements, what are the other measurements that would take in this experiment? Give them in order of measurement. There are three mass measurements we have to obtain in this experiment. F part 1, M1 mass. M1 mass is mass of calorimeter and stirrer. Mass of calorimeter and stirrer. Mass of empty calorimeter and stirrer. Then M2 is the mass of calorimeter stirrer and water. We have to pour water into the calorimeter and we have to get the second measurement. Mass of calorimeter and stirrer. Then second reading is mass of calorimeter, stirrer and water. Then third reading, mass of the system after mixing vapor. Then we can write answer for third mass measurement. M3 should be final mass of calorimeter after mixing vapor. It means it has mass of calorimeter, mass of stirrer, mass of initial water amount, and mass of mixed vapor amount. Then part 2 is the specific heat capacities of copper and water, C.C. and C.W. respectively. Write down an expression to determine the specific latent heat of vaporization of water in terms of symbols mentioned in part E and F above. Assume that there is no heat exchange with the surroundings. Now we can write the basic relationship. The heat loss of vapor should be equal to heat absorbed by water and calorimeter. Water and calorimeter. When considering heat loss of vapor, there are two methods to heat loss. First method is 100 degrees vapor is condensed to 100 degrees water. It is a phase change. Therefore, when condensing, we have to use heat energy in ml form, mass into latent heat. If there is a phase change, we have to write heat loss or heat gain as a ml term. After condensing, it makes 100 degrees water. Therefore, it should cool up to theta 3 temperature we have obtained at the maximum temperature reached by the system. When cooling generated water amount, condensed water amount, it is ms theta format. Then there are two types of heat loss in vapor. When considering heat absorbed by water and calorimeter, we know that it is ms theta type because of there is no phase change, there is only a temperature increasement. Then ms theta of water plus ms theta of calorimeter, copper calorimeter. Then we can substitute corresponding measurements. We know that mass of vapor, initial mass of empty calorimeter is N1 with stirrer, then mass of empty calorimeter stirrer and water amount we have added initially is M2. After mixing vapor, total mass is M3. Then vapor mass is M3 minus M2. And they have given that latent heat of vaporization capital A, it is LN, plus vapor mass M3 minus M2. Therefore, condensed water mass also M3 minus M2. SW is specific heat capacity of water. It is given as CW. When substituting this theta value, We know that temperature of condensed water is 100 degrees Celsius. It is cooling up to theta 3 temperature. Therefore, we can use initial temperature of vapor as theta 1 because of we have written in part E initial temperature is theta 1 but it should be 100 because of we are using steam generated in atmospheric pressure. But when considering this equation, we have to write it as theta 1 minus theta 3. Theta 1 means temperature of steam. It should be 100 degrees Celsius, but in this problem, we have to consider it as theta 1. We have obtained it as a temperature reading. Then it should be equals to initial water mass. We can substitute M2 minus M1. M1 means mass of calorimeter and styler. M2 means mass of calorimeter, styler and initial water mass. The difference of these two readings is water mass. Specific heat capacity of water CW. Water in the calorimeter is increasing its temperature from theta 2 to theta 3. Then we have to substitute theta 3 minus theta 2 as the temperature difference of water. Then mass of empty calorimeter M1, specific heat capacity of copper is given as Cc. Then temperature increasement is equal to this value, theta 3 minus theta 2. We have to write only the expression. Therefore, we can give answer like this without subjecting any other term. Then part G. What precaution would you take in this experiment to minimize the error due to heat exchange with surrounding? We can do the practical with the heat loss correction. It means we can start the practical. From a temperature which is less than about 5 degrees to the surrounding temperature. Start the experiment about the temperature which is less than 5 degrees Celsius to the room temperature. And finish the experiment when the temperature is 5 degrees Celsius more than the room temperature. It is called the heat loss correction because of I will consider if the room temperature is 30 degrees, it is the value I am using to describe, not given in the question. We are starting the practical from 25 degrees and we are finishing it at 35 degrees. Therefore, for this part, 25 to 30, there is a heat absorption to the system from the environment because of temperature of the system is less than the environment temperature. After passing room temperature, for this region, there is a heat loss to the environment. We can consider that heat absorbed by the environment for this part is equal to heat emitted to the environment for this part. Then we can consider that there is no an effective heat exchange with the environment.